Hello, 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 Tania, hello, Cynthia, hello, Leslie, hello, Lydia, hello, Amanda, hello, Isabella, hello, Crystal, hello, Farina, hello, iPhone, hello, Crystal, I got that, yes, sorry, hello, hello, Amanda, hello, Lydia, hello, Isabella, okay, I got that, sorry, hello, yes, hello, awesome, okay, hello, good afternoon, yes. Hello. Actually, is it a small class? Oh, there's more people. Sorry, coming. Okay. Okay. Hello. Oh, Arlene. Oh, yes. Hi, Arlene. Yes. I mean, sorry. Yes. Hello. Okay. Okay. Hello. All right. And I'm taking it that you can hear me. And why does it suddenly seem? Okay. No, there's more. There's more. Sorry. There's more. Okay. Awesome. Okay. Oh, I think. Oh, sorry. Okay. Right. Okay, that's right. Um, okay, I think we're all here. Oh, yes. Hello, Jamie. Hello, Miles. Hello, Rachel. Okay, I think we're all here. For some reason, it does seem smaller than, but okay. Oh, yes, there are more people. Okay, sorry. Okay. Hello. Awesome. Okay. 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 So it feels like I haven't seen you guys in a long time because I haven't. Oh, and there's more people. Okay, sorry. And that is okay. I feel like I haven't seen you guys in a while. Oh my God, there's okay. I feel hello? Okay. I feel like I haven't seen you guys for a while because I haven't, because it has been a while. But we are very much on track, and you guys are very, I mean, one good thing is, um, you know, I feel like I'm trying to have a lot more communication with you this semester than last semester, as in looking much better at your work. And more so I think it is the case that anybody who's turned in anything thus far, until today, you've gotten it back, hopefully. I mean, if you turned in something in the last few hours, then you haven't gotten it back yet. And if you have, that's totally fine. I mean, if you have turned something back recently. I think it's strange. Somehow I sent slightly different signals to this class from the signals I sent to the other class. That is, I think I was sending you mixed signals about the math methods homework, but let's say now that is actually officially due. In fact, I don't know, I'll fix it in the Google Classroom. I don't know what date it says in the Google Classroom, but that is your next assignment, and you should please try to do that, the math methods, what's called homework 2. Again, I'll take a moment in the middle of this class today and make sure that the Google Classroom is updated for that. But in other words, for some reason, I got a lot of them from some people, but very much not from. So I don't know what I said about it, but let's say now it is due, and we're still going to keep going over. We have a lot more to talk about of the last bit of homework 1. So there's plenty of time still to do homework 2 before I say anything about it. Like, you won't be cheating or anything like that, and it won't be considered late or anything, even if it doesn't come in the very next class. But I want to be clear now and say there's a section of that math methods homework. Again, I'm talking about homework 2, which I'm now saying is the next thing on the docket. Like, I think all of you have done homework 1 and you've gotten it back and all that, and the game participation points are still happening. But homework 2, which is the next thing due, there's a piece of it that's about vectors, dot products, and cross products. It's like the third section of the homework. I may have said things about this before. I have not yet attempted to teach dot products or cross products yet in this class. I will actually go over them. However, it says enough of, And I don't expect that you remember them or know them from a math class. Like some of you may have seen them in a math class and some of you have not. I'm not expecting any prior knowledge about dots and cross products. But what I am saying is that on the sheet itself, on the math methods sheet itself, or in the sheets, it gives a little definition right there of what A dot B means. Like if you have a vector A and you have a vector B, what it means to dot them. And it gives a little definition of what it means to cross them. And it gives just enough to do the exercises. It doesn't give a deep understanding of like the whys and whens and histories, but it tells you enough of a definition that if you apply the definition strictly, you should be able to do the exercises. And it's kind of like old physics 1 homework, like number line or something, where we define displacement versus distance and then say, now here are the definitions, now go. So please do that. In other words, I'm saying next homework you do is math methods, and please try to do all of it, even the stuff that looks new about dots and cross products. It's understood that that's new. You're having a first look at it right there. I mean, but right there is all the information you need. Of course, you can look up on the web for more help and stuff, but you shouldn't need to. Okay, that's with that. The homeworks, again, just keep them coming in. They're really good. Like everyone that I graded, people are doing a lot of work, and I think you're understanding things. Just as the homework gets harder, or if it gets harder, please make an extra concerted effort to circle your answers. It gets less and less tempting, but more and more important to circle your answers. Also, please know I fully tested this. I may have said this to this class already, but I want it to be clear. At any moment, like if a homework is worth 50 points, that means it's 50 points for you to get, for you to add to your grade at the end. And you can always update. You can always update. That is, especially if I marked your homework and gave like a 47 or 46 or 42 or something, it's not because you got 3 things wrong or something. It's probably because I probably wrote a note that says something like, for the full 50 points, please blah. Either like complete the problems that you didn't complete, or change a formatting aspect of it, or something picky like that. But I really do mean it. It's not a punishment, and it's not a last gasp kind of thing. Like at any given moment, even if you've gotten a grade already on a homework, even if you've already gotten a grade, if you attach a new document, people have asked this in the past, but now I've like really, really tested it, and I'm very confident and happy. If you attach a new document as per my instructions or something, even if you leave the old documents, which is preferred, but if you attach a document of any kind, even if you already have a grade and even if you already have documents in there, if you attach a new document and hit the like turn in button, it will come up on my side. That's the good news. Like you don't have to do anything. It will come up on my side as like new material that has to be graded. And then I'll look at the new document and I will change your grade to a 50. Like in other words, if I ever tell you for a full 50 points, please do this, it really is, I'm saying just revise this and then we're good to go and you have 50 points. And there's no marking it for being late or something like that. It's not an issue of being late. It's just like, I want you all to have all the points. So I'm telling you how to do. So, so don't take it as a criticism if I say that. But similarly, there's like this picky formatting thing where sometimes I'm doing that. But I'm trying to evolve as I go. So the one thing where I was a little picky on points, and I will be, but I know it doesn't seem fair or reasonable. Like I'm asking you to do your homework on separate sheets of paper. Like I give you these questions, I give you these problem sheets or whatever they're posted. And then I'm asking you to hand in your work on separate sheets. And then sometimes when people are doing the work right on those sheets, right on my sheets, I'm marking it like a 47 or a 48 or a 44 or something like that. Now, and let me explain why though, because I've been asking for this for years. This is always like a picky thing of mine, and it seems unfairly picky. But now I'm seeing more and more. I want to evolve the rule to make it easier for you. The reason I always ask that, the reason I ask people to put their work on separate sheets, like as opposed to doing your answers on my question sheets, is not because I care about my question sheets. Like I don't care if you deface them or you pass them down to your younger brothers and sisters, like for help in the future semesters. I don't care about the sheets themselves. It's just that they never have enough room on them. They never have enough space for you to actually do out your work and think fully out and show your work and make it legible. Like either it doesn't give you enough room to think and actually do what you need, or you cram your work in and then I can't read it. It doesn't give enough space. And that's the reason. So I want you to use your own blank sheets. But then the thing is, first of all, you could very reasonably say, well, then Yaverbaum, why don't you just give us enough space on the freaking sheets? I mean, give us enough space and then it'll be fine. And sometimes I've tried that, and I especially try that on exams. But the reason that doesn't work is I can't. I literally can't give you enough space because unless I give you a full whole new blank sheet for every new problem, any amount of space I give you is a finite limited section on a page that's still going to make you think this is the box for your answer. The whole idea is you should have as much space as you need and as much time as you need to work these things through. So I ask for blank sheets, but now I know this is like so boring. I'm going to stop talking about this in a minute, but that's why I've been asking that rule forever and why I always like will sort of reject homework unless it's done on blank sheets. But now I'm trying to be you these days because all this Zoom stuff and the quarantine, everything, Google Classroom is all driving us all crazy. So I'm actually now trying to do my home. I have a student file where I try to do the homework like that I'm asking you to do. And see how like much of a hassle it is on your side. What I totally realize now, I mean, some of you really do like doing your homework right on the sheets, or you cut and paste and stuff the sheets to do it on, because I realize like when I try to do my own homework as one of you, I totally see now what the problem is. I see, and I'm saying this to all of you, even if you've adapted, I appreciate to all of you that if you're trying to do my homework at all, it's really hard not to have the questions right in front of you as you try to write out your answers. Like you really want to have both in front. I see that. I mean, I want that if I'm doing my own homework. And yet, if you're doing it on a tablet with a stylus or something, or on a computer or almost anything, if you're sort of in there in Google Classroom trying to do this homework, what I'm now realizing is the reason a lot of you like to do the homework right on my homework sheet is because that way you can see the freaking question while you work it through and see that you're not missing anything. And if you start a whole new document, then you're flipping back and forth between two devices or some nonsense, and then have to do a whole attachment thing that's impossible. I actually do see that now. I didn't see that before. So this is what I want to say to all of you. The best solution I can come up with for how you can see my questions while you're trying to answer them, but yet you can actually give yourself the proper space to think and not cram everything is, this is what I'm doing now on my end. I suggest, or I ask it of you. You can take my documents, my question documents, you can turn them into a document and write on them if that's what you're doing, but just add lots of sheets of blank paper to the document. That is, use my homework as like sheet one or whatever, page one of some document that you're writing on, but then add a new blank sheet right after and start doing all the answers on the page after. So even though my questions are sitting right there, still you just turn one page to write out your answers and then do more answers on the next page until until the next page of questions. In other words, you can do it all in the same document if that makes it easier, but try still to add a new blank page. And those of you who know what I'm talking about know what I'm talking about. And if you don't, you don't. But anyway, no matter what, in the end of the day, if you try your homework and you hand in your homework, and then I gave it back to you with like a 47 or a 46 with some really picky formatting issue, and you just can't handle the formatting issue, or it's too annoying to you, or you get it and you'll do it next time. You could just write me a note and say, I understand it now. Can we call bygones bygones? And even if you just write me that note and explain the same, then I'll change it to a 50. Like it's not meant to be a punitive thing. It's just meant so we can all do this, make everything the easiest way possible. All right, that's like way too much on that topic, but I feel like you guys are doing a lot of homework and you're doing it well, and I'm trying to get back to you. So we'll keep it smooth like that. And the whole game thing still applies. Okay. Now where I feel we are in the class, I'm going to stop. I'm going to look at the chat for a second, take a moment, but where I think we're about to go in the class is back to homework one. Like I know we've talked a lot about it and we've done a lot of questions, but I believe we're up to question 9 in homework one, like the very last question. I believe, in other words, we're up to this, in effect. And I'm going to stop and look at the chat and make sure, but that's what we're going to start like solving together. Even if I already marked your homework correct and you know the answer, we're going to do this together because this really gets us into, this really opens up the physics curriculum starting with this problem. So let me just look. But okay, so that's a thumbs up. So this is where we are. Do you guys are agree? I'm looking like there's nothing in the chat. It looks like we're cool to like go from here, or let me just, are there any other questions about the class or anything, since it has been like a week and a day since we've met? Is there any obvious thing that I'm overlooking or something before I press on with physics? Yes, no, everybody had a happy Fat Tuesday, whatever, yesterday. We're all okay. So we're okay. I'm taking it from 2 people in the room Oh, good. All right, 3. Well, same person, but great. All right, cool. I'll take that. Thank you. I appreciate it. Thank you. All right. So we're here. According to the homework question, t equals 1 second. What does x equal? So like according to homework, we're trying to find a number in meters. But what I want to say is, since this is there's nothing special about this actual spring. It's a fictional spring. There's nothing special about the number 1 second. What's really going on in this question, what we're really being asked now is, what is x as a function of t? Like we are looking, we'll get a number easily once we have some kind of algebraic or mathematical expression that has a bunch of letters and or maybe numbers in it, and where one of the letters is x separated by itself and one of the other letters is t, some kind of rule where if you plug in t, we'll be able to tell you what x is. That's what we're really looking for here. Like something that will work whether it happens to be t equals 1 second or 2 seconds or 3 or whatever. So we seek, x as a function of t. Now, that's what question 9 is really about. Now, that's a fair question. The reason it's on homework 1, even though we've spent like 2 weeks on it already, it's a fair question because it's like what physics is always about. You name the time, I name the space, or vice versa. You name the place, I'll name the time. Like given some baseball that's doing this right now, how many seconds will it take the baseball to reach home plate? Or in 5 seconds, where will the baseball be? Or in 5 seconds, where will the cannonball be? Or the space shuttle, or whatever. Like that's what physics is always about, is what is x as a function of t? And we were doing what is x as a function of t like a bunch for the first like practically half of physics 1, of physics 203. We totally were always solving for x as a function of t, only frequently we were plugging into an equation that we had to answer this question. We had x equals 1/2 at squared plus v naught t. Like that, often that was the answer that we were looking for. But that was under particular conditions. Like that was the beginning of physics 203. The answer to what is x as a function of t was, well, x equals 1/2 at squared. That's what function of t it is. That was often the answer because what we were first learning then is situations where acceleration is constant. As we, just to like review, as we spent the first 3 questions of this problem, of this homework sheet, the first 3 parts, question 1, 2, 3, were all about acceleration and force and thinking of moments about acceleration and force because that's where physics begins. But then suddenly we realize in the middle of this sheet, oh, acceleration is changing from spot to spot and from moment to moment. So, okay, we can't use the acceleration, the constant acceleration model anymore. We go to the next step in physics and we started thinking about, oh, not constant acceleration, but constant energy. And we did energy conservation for the next like questions 4, 5, 6, 7, 8. We were doing energy conservation. And that was working because even though the acceleration, well, because acceleration is not constant, force is not constant. When force changes from place to place, we say the energy is constant. So we did that. But now we're up to question 9. And the energy method is no longer going to work for us either, any more than the constant acceleration method. Like we're up at question 9 and we still seem to have a very simple question in physics. What is the place given the time? The reason we still don't know off the top of our heads is because energy tells you about things from place to place. It relates speed from place to place, or relates place to speed. Energy doesn't relate place to time. Energy always looks the same. Energy conserving systems always look the same in time, whether you run them backwards or forwards, like we talked about that. So we have this really simple question. What is the place given the time? And we have these conditions that seem really simple and patterned, back and forth, back and forth, back and forth. But those conditions are just new enough and just complicated enough somehow that we don't yet have an obvious answer to what x is as a function of t. That is, so here's the next page. What we're saying is it's still physics. This is still like, this is still physics like it always was, like physics 1, physics 2 or 3, because we're still looking for position as a function of time. The new conditions of the physics, the new like physics facts that now make this a new chapter are that not only is A not equal to A naught, like not only is A changing now, but what we specifically know is how it's changing. We know the one given we have here is a spring following Hooke's law, like the spring law. the one thing we know now is that the force, even though it's changing from place to place, it's changing in a linear way. That's the one fact we have, that this linearly, this linearly changing force is the only force acting on the mass. Therefore, it is the net force. Therefore, the new physics condition, like we've had physics law, F net equals ma for a long time. Like that's just the second law of motion from Newton that says how all forces always are going to work. Now we're specifically saying the one specific circumstance we're investigating here is the specific force called the spring force, the elastic force. And when it is the only force acting, when it is ma, that is a situation that we should be able to analyze. We should be able to predict x as a function of t, but we never have yet before. So what are we going to do? We're looking for x as a function of t. The only statement from physics we have has an x in it, but it doesn't have a t in it. Instead, it has an a. So do I know any relation between acceleration and time? Like I'm asking myself, I'm asking myself, well, by definition, instantaneous acceleration is the instantaneous rate of change of velocity. Like instantaneous acceleration is the derivative of velocity with respect to time. And what's velocity? The derivative of position with respect to time. So this is where I have here. I'm going to pause for a second just to make sure. I mean, because I know I'm sort of like, I almost feel like this is a PowerPoint presentation or something. But what I'm trying to do now, remember, I'm looking, what I'm doing now is what I would do if I were doing this. Like, this is the optimal version of what you did if doing this problem 9, assuming you didn't already know how to do it going in. Like some people have had backgrounds where they go into question 9, they already know some things about it. That's fine. But if you don't know what to do, like, what do you do? Well, what you do is write down what you know. All we know is f equals negative kx and f net equals ma. And then try to relate that to what you're looking for. We're looking for x as a function of t. What we have is a statement that relates x to a. So I thought in my mind, how is a related to t? Oh yes, acceleration is the second derivative of position with respect to time. Notice, like I'm going to use this. I've noticed it's a triple equal sign. I mean, it is kind of the key to unlock this situation or to begin unlocking it. But notice I'm using it. I'm not, like, what that says is the definition of acceleration is that it is the derivative of position with respect to time. It's not taking a derivative is what I'm trying to say. Like we might end up taking some derivatives, but I'm not taking any derivatives yet. I'm making a substitution. I'm simply saying that when I see a here, when I see that a, if I'm trying to think of some ways to relate it to like t, or particularly to x and t, I can remember that what a is the same as is the second derivative of x with respect to t. So that a is that. So I'm making a substitution is what I'm trying to say. I have to know enough calculus to know to do that. I have to know the definition of derivatives in calculus, but I don't necessarily have to know how to take a derivative to do what I've done so far. So I make that substitution, and now we're going to pause. What I'm saying is, just by making that substitution, according to the physics, then just according to definitions, I now arrive at a physics statement that looks like it has, like this is about as far as I would sort of dream or hope that someone in their honest, if you look at question 9 on homework 1, and you have never done it before, like you're in physics 2, you know, for the first time in your life, as you should be, and you haven't taken 85 million math courses that you didn't need to. If you're looking at question 9, like hopefully you would know that you can't say x equals 1/2 at squared because we don't have an a anymore to plug in. Because a is changing, we have to do something else. So we look at a itself, and I feel like if you can get to get this far, take some thought. But hopefully if you see what I'm saying, it makes sense. It's like so far, I'm not using any new knowledge or new information or even new tricky knowledge. I'm just putting together old knowledge to say, now I've got an equation. It looks like I've got an equation that has a bunch of letters in it, like no numbers, but you know, secretly K stands for a number, right? K stands for 200 newtons per meter in this problem. And M secretly stands for 300 grams or, you know, 0.3 kilograms. They basically are numbers. That is to say, K and M are what we call constants they're letters that stand for numbers. They might as well be numbers. We just want to be able to recognize that whatever truth we find here is true for all numbers. But x and t are not constants. X and t are not numbers. They are the variables, and they're exactly the variables we want. Like what I'm pausing to say here, and then I will pause, or I will really go on. I'm saying that I have not solved problem. We're working on problem 9 here. I do not feel that I have an answer yet, but I feel like I'm progressing towards something because I now have an expression, and the only variables in this expression are x and t. Those are precisely the variables that I do want to relate to each other. And furthermore, they're not in the right places. Like we're not done, but they're sort of being treated the right way in that x here is found in the numerator and t is found in the denominator of a derivative. So I know that this expression is treating t as an independent variable. That's what I'm trying to say here. And it's treating x as a dependent variable. And that's the treatment I want. Like we're looking, we'll know we're done when we get x on the left hand side of something and a bunch of stuff on the right hand side, all of which includes t. We want x as a function of t. We want x to depend on t. So the way this is written is good news. It is treating x as the depending thing and t as the dependent, but that's as far as I'm getting so far. I haven't solved this. I haven't said how to solve it. It's not solved. It's just an expression. I'm going to go one step further to clean it up. I'm going to collect all the constants. I'm just going to clean it up a little bit. Wait, is this exactly what I just said? Yeah. So I'm just recopying it here. But then I'm going to divide both sides by, well, yeah, I'm just rearranging and dividing both sides. Excuse me. I'm dividing both sides by m, and then I'm flipping both sides so that I can write it like this down here. I'm going to pause again. And by writing it that way, I haven't changed the content or anything. I've just sort of put all the constants together in one term to sort of make it clear that that whole thing in parentheses might as well just be one big number. It's like the number 200 over 0.3. You know, it might as well be 60 or whatever. And the thing on the left is the most intimidating piece of all. It's some kind of second derivative. But this is my cleanup version of this expression. This is what I know so far. It is not an answer. I'm looking for x as a function of t. What I have here is the second derivative of x as a function of x. Like it's the same information ultimately, but related in a totally different way, which is why I'm on the right track, but I'm not done. That's what I want to say so far. Are we like so far? Am I clear? Is it clear where we are in this thing so far? Like, could I get either a thumbs up or a thumbs down or something? Like, does it make sense what we have so far? Okay.
Yes, it does.
I totally appreciate it.
I have a question.
Yes.
First.
Yes.
So when we're doing this, we're looking to have in the equation that we're using to solve this problem, we want the independent variable on one side and the dependent variable on the other side? Or is
Yes.
it just for this question?
Oh, no, exactly. No, that's perfect. In general, I'll know that I'll have the best feeling that I'm done. I'll know that I'm done if I end up with an expression that has, yeah, the dependent variable on one side. That's what I'm hoping for. That's what I'm trying to get. Yes, the dependent variable on one side and the independent variable on the other side. That is exactly right. And to be even more clear to everybody, I mean, to even add to that, like there's going to be other stuff in the expression too. Like they should be on different sides. Now, one of them will be separated all by itself, ideally. Like ideally, the dependent variable x will be like by itself. I'll know I'm done when I literally have. So yeah, in fact, let me just write this down. That's totally is an important point. Like this is a super important point, what Ardell is saying. Like, yeah, and this is what, because we are about to get more mathy in our physics and more physicsy in our physics. Like the kind of answer we're really looking for here in question 9. I mean, ultimately we're looking for a number, sure. Like ultimately we're going to get a number of meters where the thing was at 1 second. But where we're going to get, what's really important is our second to last step, where we're going to get some kind of actual formula, like something that looks like a physics formula. We're looking for some expression where x is by itself, literally x is by itself, literally on the left side, and then equals some blah, 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 like rule or something that we're going to do to t. Like it might be like 5t squared plus 7, or it might be like 5 cosine of t minus 9, or it might be like 5, like 5 t to the 5th power over tangent of 9 or something. But it's going to be definitely what we are absolutely looking for when we say we're looking for x as a function of t is exactly what Ardell is saying, that we're looking for something that will separate out our x's and our t's, put them on different side of the equation, and tell us a rule to do to one in order to generate the other. So specifically, last thing I'm saying on this is whatever is here is what I mean by the dependent, and whatever is here is what I mean by the independent. Like for us, generally time is the independent variable, but it doesn't have to be in life. That's not a rule for Moses. What's a rule is the thing that you do the rule to is called independent, and the input is called independent, and the output is called dependent. And for us here, that's x is the dependent, t is the independent. And why this is so important, like why I'm staying on this. All right, so hopefully that, and tell me if that doesn't answer that, but yeah, we're looking for our answer. Like people, again, why this is important, actually, another way to put this is the thing that we're going to find that we're going to call our final answer is what we might be used to from chemistry or biology, thinking of as the formula that you would plug in to get the answer. Like what we're trying to do here is come up with the formulas. They are our answers. And we'll know that we're there when we have a formula that looks like x equals blah, 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 t. However, what we have, and here's our challenge, I mean, to bring us back to this, what the physics tells us from the physics laws is we don't have a rule x. We don't have a rule by virtue of which you could plug in a t and get out an x. What we have is some rule about the second derivative of x with respect to t equaling, like this rule says, well, I'll tell you, if you plug in x, I'll tell you what happens to the second derivative of x. And we're like, well, that's great. And that's got to be related somehow because you're saying the second derivative of x with respect to t, like you've got an x and a t in what you're saying, but you're telling me if I tell you the x, you'll tell me like well, look, I'll put it in English. Here's the problem. What we're looking for is a rule by virtue of which you tell me the time, I tell you where we're going to find the mass, like how many centimeters out from the equilibrium position. Like remember, this mass is going blah, 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 blah. So we're just looking for a simple rule. You name the time, I tell you where the mass is. If you say it's 1 second, I'll be able to say it's like it's over here. If you say it's 2 seconds, I'll say it's over here. That's what I'm looking for. What do I have instead? I have something that says, I have something here that says, oh, here you go. You tell me where it is, and I'll tell you the acceleration. And I'm like, the acceleration, that's not what I'm asking. I'm asking just like, where is it? And you're saying, well, I could tell you the acceleration. And then maybe I think to myself, oh, well, actually, that's not so bad. I mean, it's physics. If you tell me the acceleration, I suppose, like from 1/2 at squared and stuff, I suppose if you tell me the acceleration, that's pretty useful. I could use the acceleration probably to figure out how fast it's going and use that to figure out where it is. So tell me again, how are you going to tell me the acceleration? What do I need to tell you? So if I tell you the time, you'll tell me the acceleration. Is that what you're saying? And you say, no, I'm not saying that. I'm saying, you tell me where it is and I'll tell you the acceleration. And I'm like, where it is, that's the whole thing I'm asking. And in fact, I even believe as a physicist that where it is probably depends on acceleration. But you're telling me the acceleration depends on where it is. That's what this thing is saying. Okay, it is saying all the information we want, but in this wacko way that is actually kind of circular. This thing is literally saying the rate at which x depends on t, depends on x. That's what this thing is saying. This thing, in other words, is worth dwelling on. This thing that we now have, that the physics has brought us to. Okay, we didn't invite this thing in. We didn't sign up for this or register for this as a class and have prerequisites or whatever. The physics said some simple things like, here's how forces work and here's how force on a spring works. It's linear. So it goes back and forth, very simple, back and forth, back. And now the physics is saying to us, what we have here is an example of something called in math a differential equation. This is a differential equation. I'm saying that explicitly. This is what's called a differential equation, not just an equation that has derivatives in it, or not just an equation where you have to take derivatives or something. This is something called a differential equation. There are entire classes in math departments called differential equations. In fact, there's classes called ordinary differential equations 1, ordinary differential equations 2, partial differential equations 1, partial differential equations 2. There's things called first order, second, blah, blah. Now, before we go any further, the reason I'm stopping cold on this, as I do every semester, is because I love this, is because I want to make it clear to anybody who's listening. I did not expect you to take any class ever before this one called differential equations. Not at all. It was not a prerequisite. In fact, the calculus prerequisites that you do have weren't even my idea in the first place. I don't even believe in them. Okay. It is not a prerequisite that you have seen a differential equation before this class. In fact, I'd strongly prefer that you hadn't. If you have seen one, that's great, but don't let the prior knowledge like bog you down. Please come with an open mind or whatever. I'm expecting that people have not seen differential equations before, which is why we have a chance at actually maybe appreciating them before they become total pain and have all the music taken out of them. A differential equation comes up naturally to us the same way it came up naturally to Newton and Hooke and people who didn't have math classes to learn the stuff from. They just made things up that worked. As we're going to do, or they realized things that worked as we're going to do. What I want us to appreciate here, again, and you're not expected to know anything about this. I'm telling you what I want you to know about this, or we're going to show each other. This equation right here, the reason it's given a special name is because it is weird. It's saying something weird. This thing is saying that that the rate of change of the rate of change of some effect with respect to cause depends on not the cause, but the effect. That's what this thing is saying. Like it's saying, in other words, what makes this thing, so this thing is technically called, and again, I'm teaching it right now. It's not, you didn't know, I'm teaching it now. It's part of the physics. It happens to be called a second order differential equation because the kind of derivative that you see on the left-hand side happens to be a second derivative. Again, that just comes up because that's what nature spits out at us a lot is second derivatives. But why is it called a differential equation at all? Like, what is the thing with this? Is that it's an equation that presents us with a derivative, but it says that the derivative is related in some way to the dependent variable. What makes this an interesting equation, what makes it like worth studying on its own to some people who like studying equations on their own, is that it's relating a derivative to a dependent variable rather than an independent variable. It's like relating a rate of change to effect rather than to cause. Let me be more specific what I'm saying. I'm saying, well, yes, here, okay. So you might want to write this down or whatever. And I'm going to go back to that other page in one moment, but I'm saying we call something a differential equation if a derivative of some dependent variable is presented as a function of the same dependent variable. There's a lot of weird different ways to say the same thing. I'm gonna go back and forth between these two pages for a second. So I mean, and you can stop me, but like we're about to do some math. And again, by the way, I know some of you, a lot of you didn't know what, you could do the steps up until where I did them just now. Then at that point, you may not know what to do next. Honestly, most of us should not have known historically what to do next in solving this question 9. There's things to think through and figure out, but there's no expectation that you had already seen this problem. So some of us stopped right there, which is honest, and said, I can't go any further. I don't know what to do. And I wrote some things down. Some of us stopped even before that because we didn't even want to get to that point. Some of us went on the web and did things and found things, and some of us have thought about this before. So, and that's cool too. Some of us went on the web and wrote down things that they got from the web from here. Some of us who got things from the web looked and then saw and was like, oh, I guess that makes sense. I didn't think of it before. I had to go on the web to find that, but now I get it, and then wrote it down. That's cool. Others of us got some things on the web and were like, I don't really know. I guess I was supposed to know this. I guess this makes sense. Maybe Yaverbaum thinks that I know this, but I don't. And then wrote it down. And only we know who we are. And some of us like just blindly, of course, were like, what? And wrote it down. Whatever person you are, that's between you and yourself, right? Like, you know how much you understood what you wrote down. But what I'm here to say to everybody is, let's unpack that stuff that was found on the web. It's not just knowledge. It's something that someone's thinking through. We got to do the thinking through together. So the first thing I want to say is, concretely speaking, like, in order for us to solve this equation, and that's what we have to do, we have to do something to this equation to get the x's and the t's separated so that we get what Ardell was saying before. Like, what we're looking for is an x by itself and a t by itself. It is not obvious looking at this what to do. Hopefully it's apparent that something could be done because this thing has just x's and t's in it. But like, what can we do? I should back up and say what we can't do is just divide both sides by x. Like, if you put that in homework, I'd give you tons of points because it means you're actually trying something and getting it, but it wouldn't ultimately be right. It won't get you the right answer. You can't divide both sides by x because, like, what's on the left is a derivative of x, right? In fact, it's a second derivative. It's not something being multiplied by x. It's an operation being performed on x. So you can't. So the question is, what do we do, right? What do we do to get x by itself, t by itself? The first thing I want to say is, you might have thoughts, and they might be very good thoughts, but why we have to have thoughts at all is this red note right here. I don't know if you could see. Yeah, this red note right here, what I'm trying to say is, if this x right here weren't an x but a t, if you left everything else the same in this equation, like if this were a math class where we're just making math expressions up, if that x were not an x but a t, then we would not call this a differential equation. I want to make this very clear. Even though it would look just the same, it would have a derivative on the left side. It would like look like calculus and all that. But if this x were a t, then it would be an equation that had a derivative in it. And in order to get t to get x as a function of t, we would do what a lot of you would maybe guess. We would do the derivatives of this backwards. We would do inverse derivatives, i.e. integrals. We would integrate this twice and we'd have an answer and we'd be done with it. It might not be fun, but it wouldn't be a big deal and we wouldn't call it a differential equation. If this x were a t, this wouldn't be worth a whole class or 2 weeks. But this x is an x, and it actually means very interesting that this is an x, not a t. It literally is the reason that this is called a differential equation. The fact that the derivative is being presented as a function of the dependent variable makes all the mathematical and philosophical difference in the world. And I am making a big deal, and like, sorry, I don't mean to be yelling, like I'm not angry at anybody, obviously, but I do want to make a ferocious deal of this. So I'm going to go even one step further. Wait, what time is it? Wait, let me see.
And some of them got ready.
It's 3:48.
No, thank you. Oh, sorry, that wasn't. Wow. Yeah, I actually caught that, and then I heard the voice. But wow, talk about paying it. Thank you. Yes, it's now. I'm so excited. Probably 3:49 now, but thank you. So yeah, we have to accomplish 2 things before the class ends today. We are still on question 9 of homework 1. I'm very aware of that, and again, that's why you're not going to get like a homework sheet 3 for a while or something. But this is like the way it goes every semester. This is all not a digression. This is how important question 9 is. And question 9 is the point of the whole sheet. So we have to do 2 things with this. One, I have to try to explain to you in English what the mathematics of this is. But 2, we have to do the mathematics. So in fact, let's do it in that order. So what I'm going to say right now, we have some time left. I don't want to confuse anybody. This is still in the context of solving question 9. Like, we are going to solve it together. I'm trying to show you why we have to be careful about solving it. Why, basically, I want to show you is why some methods of solving it don't work. So in order to do that, I want to show you what it means that it is a differential equation. In order to appreciate this, like I want you to see the difference between an equation that just happens to have a derivative in it versus this kind of arrangement that we call a differential equation. So what we're going to consider now, and this will probably take us to the remaining of this period. So again, in advance, I apologize. If we finish this period and we're all still discussing this counter example I'm about to give you, this is a do now. This is like an example that we're doing together now in the class, and we can get class participation points for, yay. And it'll stop me from talking, yay. But it's still all a do now that we're doing in the context of me trying to explain how to do number 9. Again, all of this shows there's no way I can take off points on your homework if you didn't finish question number 9 and get the right answer. Like, there's almost no way I could expect you to do all of question 9 with all of these thoughts that I'm unpacking. I couldn't be grading you on the expectation that you would do all of that. You get the full points if you tried it. But I do want you to see when we're done with this whole procedure we're going to do, hopefully you all see that it makes sense and that it was possible for every one of us to do it if we had nothing better to do in our lives. So this is all in the question, all in the context of solving question 9 of homework 1 as part of that. Right now, what I all want as a fresh new problem, I'm giving you right now to everybody to solve. So, and so one thing I'm going to ask is try to solve this right now. I'm going to keep talking, but like as soon as you get what I'm saying, like tune me out, try in your individual private Idaho to solve this. Put in the private chat, put any answer you might have or any question, or if you're just done, like once you think you're done and you're not thinking anymore, put a thumbs up or something like that, just so we know you're done. But in other words, if you actually have an answer, you don't have to share it publicly. You can share it with me privately. But I want everybody to try to solve this. What is this? It is look at this equation that kind of looks like it's like a simplified version of the one that we just stumbled on in question 9. This says, imagine that there's some dx dt, which equals 5t, right? Like I'm giving you derivative. And I'm even giving you one other fact, just like in the spring, I give you the fact that the mass starts at a position that we call x naught, 0.15 meters. So imagine that the very first value of x, like the value of x when t, in other words, when t equals 0, x equals 7. So I'm giving you these two facts. One, that dx dt equals 5t. Two, that when t equals 0, x equals 7. What I want you to do for this as an exercise, this is tell me what x is as a function of t. So it's the same, that's what I'm asking you to do right now. It's the same goal as we have in question 9, only here, first of all, I'm making it a first derivative rather than the second derivative, so we can look at things more simply. But also here, I'm on purpose putting, you'll notice I'm saying dx dt equals 5t. I'm not saying equals 5x. So I'm showing you something by a counter example. So I want everybody to try, you're solving for x as a function of t. You're going to get some formula, some expression where x is by itself on the left and a bunch of things happen to t on the right. And you're using these two facts to get that. So again, once you are either done or you've run out of ideas, like put a thumb up or whatever. But if you think you have an answer or something to share, please do, but do it in the private chat. So then, awesome. Everybody take your time. And again, I'm glad I'm seeing stuff in the private chat, but I'm glad people are doing the private chat because everybody take your time for a second. Make sure you understand what's going on. So again, yeah, we're looking. And there's also an opportunity, anybody who wants to even put in the chat, I get the question, but I don't know how to do it, or so, feel free to anything. But I do hope I am asking the whole group a question. Oh, cool. Oh, and I'll say for this, wait, I just got more in the chat. Your answer to this, and again, this is also a place where I'll give, participation points for wrong answers, right answers, whatever, but I don't think your answer to this will be a literal number. It's going to be some kind of expression, like x equals blah, blah, t, blah, blah. I don't think, yeah, you couldn't get a number unless I specified what t actually is. But in a minute, I will. This ends at 4:20. I know I always think it's right. So we do have time. So I'm going to give it a little more. And I'm actually going to add something to this. I don't want to, anybody who's still working, please keep working, but I'm going to go one step further for anybody who is already on top of it. So again, what we're doing, and I will stop and explain in a second, but what we're all trying to do as a class is this thing that's on the board right now. And if you are thinking about it, please keep thinking about it. If you think you've already thought about it and you've already gotten an answer to this, then where this is going, or so that everybody can see the context here, we're going to compare and contrast the answers to this to this question. What I'm trying to say to everybody, I will shut up again for like one more minute to let everybody think, but I'm trying to say there's a very big difference in a problem set up like this versus this. They're very similar. They're like identical, except one has a T and one has an X, right? And what I'm here to show you is the different things that happen once it's an X there on the right side. So right now, what we're all going to try to do, well, I'm going to shut up for like one more minute, but we're trying to solve it. What happens if there's a T on that side? So I'm going to shut up for one more minute, and then we're going to go. Okay. Well, okay, yeah, I'm gonna, well, here, I feel bad. This is how I solve. Oh, sorry. Oh, yeah. Wait, so which page, sorry. Is this the page? Oh, okay. This one? Okay, yeah, okay, cool. Okay, so this is good. People are clearly with me. Like I feel the people in the room. So, but I'm going to talk this one now. Some people got answers, but a lot of people didn't. So I'm going to go over this one first. Okay. Now, the reason I'm going over this, and I want to be careful, like this is like anything else. Once you see it, hopefully it'll make sense and you'll be like, oh, that's not that big of a deal. But I want to acknowledge this is a weird way of thinking. Like I'm not showing you a mathematical procedure. I'm sort of trying to show you a backwards. The main thing I'm trying to show everybody today is what does it mean? What kind of answer are we looking for? How do we even know once we've landed that we have an answer? We're in a situation now where the answers that we're looking for are equations. We're not using equations to solve for numerical answers. The answers we're looking for are equations. And what we're generally being given in order to get those equations are derivatives. Okay, like that's the land we're in right now. But we have to be even more specific than that. So I'm showing you two different cases of two different kind of derivatives that we could be given and what we would do. So here's case one. Say you're given, like, yeah, like we're assuming that t is an independent variable, like that's what we're assuming here, and x is a dependent variable. X depends on t. But the information we're given, now imagine we got this information from collecting lab data or something like that. Like somehow we don't know any rule that links x to t. But what we know, assume, is that the derivative of x with respect to t equals 5t. And we know one value of x. We know that when t equals 0, we know that x is 7. Like it's like we have 1 point on the data. We know one data point on this line, and we know the slope of the line, in effect, or the rule that it's not a line, it's like a parabola. But and we're looking for what the function is. So what do we do? What some of you might think, or some of you did think correctly, is, okay. You might think he's looking for a function. He doesn't have the function. He has a derivative. He wants the function. He has a derivative. So he's not going to take a derivative. Like, by the way, that's correct. Like, I have a derivative. I'm looking for the function. So I'm not going to take a derivative. I already have a derivative. I don't want to differentiate it. I don't want to make it more of a derivative. So you might think, oh, you want to go derivative backwards, don't you, Yaverbaum? Yes, I do. So you might think, oh, you want to integrate because the integral is the inverse function of the derivative. And that would all be true if that's what you're thinking. Somehow, if I have the derivative and I'm looking for the function, somehow what I'm going to do is going to involve integration, I think. Again, that's correct if that's what you're thinking. But now I want to be careful about doing it. So like I can't just like take integrals when I feel like it. In fact, well, not only am I not allowed, but actually the hard part about math, the actual part that we all should respect in calculus, is like even when you get a good grade in the class or you do a lot of work and stuff, a lot of times a lot of people know how to take derivatives and even know how to take integrals, but for the life of them, they couldn't tell you why or when to decide to use an integral, right? To decide to just introduce an integral is like what the math teacher does. And certainly that's the way I felt about it forever. Like, don't ask me why the integral is coming up, or don't ask me to decide when it's coming because I'll have no idea. I'll be lucky if you give me the integral and maybe I can tweak it through. What we're saying here is that's right. You can't just like bring up integrals whenever you feel like it, even if you think they're going to work. You have to be proper. So what do? This is what we do. So I'm going to solve it. I know I had a page already. I'm just going to do it fresh here. We have this, right? This is what's given. We have this. I'm using the first piece of information first. We're looking, we want x as some kind of function of t, right? Just reminding you. So what can I do? The most proper thing I could do, really the only kind of right thing I can do first is multiply both sides by dt. That I can do. I can go like this. You might not think to do that. You might not think you can. You might not think you have to, but you can and you have to. Because now, by doing that, like, first of all, remember, a derivative is just a ratio of differentials. A derivative is a ratio. It's like a slope. A derivative is rise over run, delta y over delta x, only in the limiting case where delta y and delta x are so small that they're dy and dx, that they're infinitesimally small. But a derivative is a ratio. So you multiply both sides by the denominator of that ratio. And the reason you do that is because now I've got two expressions that are integrable. Like, I can integrate that side as long as I integrate the other side, and I can integrate both sides because, look, now what I have on both sides look like things you would see in a math class. And I'm getting recognized. Like, I know we've all seen integrals in math. I know how we secretly feel about them. It's not a secret, right? I'm not assuming that you feel comfortable taking integrals or whatever, but I'm assuming that you take enough that you actually, even if you never like that little dx that's always sitting there in an integral, or that dt, like, you know, and I know you're not even allowed to think of it as an integral unless it has both that sign and a d something in it. And the d something tells you what the variable of integration is. Like, it's what makes it specifically an integral of something in particular. Well, I did this step so that I could do this step. Now I've got two things on the left hand and right side of this equation that actually look like things that could come up in a math class. I don't have any like limits on these integral signs. Like, I don't have anything here and I don't have anything here. I mean, I could make something up, but I don't want to make anything up. I don't have it. So I guess these are indefinite integrals, and they are, and that's okay. I know how to do indefinite integrals for math class. Like, let's do it on the left, just like the left side. If you just walked into a math class and was on an exam and they said integral of dx, like, solve. What is the integral of dx according to math? Like, what's the left side is what I'm asking.
X.
Yes, awesome. And by the way, I have the wrong view on it, so I didn't even see. I don't know if that was, but yeah, yes, yeah. That, oh, awesome. That's right. Okay, great. I mean, did I say that's what I thought? Did I say that's who I thought? That would be rude. I didn't think I did. Okay, that's yes. The integral of dx is x, almost by definition, or you could think of it as the integral of x to the 0, which is what, however you think of it, that's right. And then maybe somebody else. What about the right hand side? One step level more exotic, but it's still just a power rule taken in reverse. If you like, could somebody else tell me? And I'll change the view so I can even tell the right hand side going once, going the integral of the right hand side. Make a math teacher proud. Honk if you
T squared over 2.
awesome. Even though I didn't, yeah, you said yes, and with the 5 as well. Yes, absolutely awesome. Yes. In fact, I'm just going to add this little step just to write it. Like, the 5 is a constant, so I could take it out if that makes anybody happy. For some people, that makes me. But then I totally agree whether I took it out then or not. What Billy's saying, and it is Billy. I think that was Billy. Yes, is he's saying this? Yes. So now we're almost done. But now one thing I kind of cheated a little bit a second ago when, I mean, I'm not changing this. I still agree with Ardell like every day, and I agree with Billy over here. But one thing I had a second before that made a big honk and stink, or a big stinking honk, that these are indefinite integrals. So if this were a math class or I were a math teacher, of course, I would be all picky and say something like that, right? And then I would actually technically have to do something like that to the right side too. Like, each one of these is an indefinite integral. So each one of them is going to produce a plus c, right? Which I know, again, is one of those things in math that maybe we never always felt comfortable with, but I know you're used to, right? But now it's going to be a different c. Like, c just stands for some number that I don't know, but that isn't going to change. I don't know it, but it's not going to change, so I call it c. Well, whatever it is, I don't know. On the left-hand side, I have no reason to believe it's going to be the same one as it is on the right-hand side. So if I want to be really careful, I better do something like this, right? So now we're almost at an answer here. I hope everybody's with me. Like, I'm just trying to be careful about how I unpack something that has a derivative in it. I have this so far. I'm almost there, but I'm looking for an answer. I'm looking for a rule where you plug in t and I'll be able to tell you what x is. I'm almost there, but I don't know what I mean by C1 and C2. Like, that's no kind of rule until I can figure out what I mean by C1 and C2. So we're going to keep going for a second. And again, if this is all we get to today, it's fine, and I wouldn't be surprised. But sorry. So I'm just recopying. We have this. I believe this is what we have so far, right? Right. And again, please, anybody stop me if, but now, like we'd be done. We're looking for X as a function of T. So we'd be done were it not for these pesky C1 and C2. Like that's not good enough. I can't leave my answer that way because I don't know what they stand for. And there's two of them. That's super annoying. So first thing is, I don't like the fact that there are two of them. Why don't I do this clever thing? I'm going to do this. I'm going to say, you know what? C1, and this is an important like physics trick that's going to come up a lot. I mean, math trick, whatever you want to call it. But I'm saying C1 stands for some number that I don't know what it is, but it's a number. C2 is some other number that I don't know what it is. Well, some number that I don't know what it is minus some other number that I don't know what it is equals some third number that I don't know what it is, right? Like if the first one's 7, the other one's 3, then the difference between them is 4. I still don't know what it is. So I might as well just define C3 to be the difference between C1 and C2. And that way, at least I can go something like this. I can say, or sorry, even better. Sorry, C2 minus C1, let's say, it doesn't matter. C2 minus C1. So I'll say, oh, then at least by doing that, even though it seems like a cheap trick, now if I subtract C1 from both sides, then I've suddenly just reduced the number of unknown things from 2 unknown things down to 1. It's a trick, but it's true, right? There's one thing I don't know, this number, that's the difference between the other 2 numbers. But by the way, as long as if it's only one number I don't know, there's no reason to call it C3. That's clunky. So I'm going to go back to calling it C again. Just note what it seems like black magic. Well, I don't know what it seems like, but this is an important way of thinking that's going to come up in other problems. So far I have, whoop, have I been writing the wrong thing? Oh, yeah. So this is what we have so far. We're almost there at an answer. But remember, again, I was looking for a function of t. We have a function of t here. X equals 5t squared divided by 2 plus c. So like if you tell me t, we plug in and we get x. Only problem is we still don't know what c is. How do we solve for c? Well, it's one piece of information that's missing here that we're solving for is c. But remember, not coincidentally, the original problem gave us 2 pieces of information. The original problem we were originally given this. And that's what we've been using this whole time. Like this is that's the thing. We multiply both sides by dt. We integrated, like that's where we're getting all this nonsense. But we were also told this, what it seemed like, you know, side information. Remember, I noted like it's like with the thing on the spring that we're not just told that we have a spring of a certain K, but we're told what the initial position is. Similarly here, we were told the initial position, and that's a piece of information we have not used in any way yet. So let's use it. Now, again, I'm showing everybody something here. I'm not expecting that you were walking around doing this problem before today. Like I'm showing you something, but I think it's reasonable once you see it. I'm saying, oh, no, I'm not. I'm saying, oh, we have so far that x, remember, we're looking for x as a function of t. Seems like math because it is. We have this so far, and we just reminded ourselves that when t equals 0, apparently x equals 7. Like that's what we mean when we say x of 0 is 7. Or put another way, that's like saying x naught equals 7. All the same thing, right? That initial condition was the other piece of information that we were given, and for this reason, because now we can literally plug it in. We can apply, when t, like when t equals 0, x equals 7. So apparently x equals 7 when t equals 0, right? Not apparently, because we were told. So I'm plugging it into that equation. This is kind of like using point slope formula and 1 point to get the line in y equal. No, it's nothing like that at all. I don't know. It's like math. So what we get is 7 equals 0 plus c. What does that have to do with anything? Well, therefore, I guess 7 equals c all around the mulberry bush. Like at this point, if I'm anybody in this class besides me, at this point, I'm lucky if I remember what the original question was, right? I know that's the only thing about physics. Like, can I just pause right here? If you're still with me, but you've totally lost me, like if you're still with me, but you're like, I have no, like, yes, I'm copying you, Yaverbaum, but I don't even know why we are on this journey or what this has to do with, right? That's the hardest thing of physics is just keeping track on, which is why we write everything down. Because me too, I barely can remember why this is all happening. But as long as I remember that every single one of these steps is a baby step, every little step makes total sense. It's just a matter of keeping track the pile. Well, while all this is happening, the pile is that we're looking for x as a function of t, and we're almost there. We have x as a function of t. It's just the one unknown, like the one annoying piece of information there is this reference to c, like this thing that we made up in the middle that doesn't have any, that needs to have a value for us to be done. But we just took this side journey to get that value. We used the initial condition to get that arbitrary constant. That's actually like a rule. So we got that constant c actually stands for 7. Therefore, our answer is Therefore, our answer to this business okay. First of all, this is what I mean by an answer to this exercise. This is, what time is it? This is almost the end of class. This is an exercise I just made up. This is a let me be very clear, or as clear as I can before class is about to end. Question 9 asked us to get x as a function of t, given that d2x dt squared equals negative k over mx. Like question 9 ended up saying to us, you solve for x. Oh, well, you solve for x as a function of t. The question 9 ended up saying that. I know we're just about to wrap up. Question 9, by the time we get to it and look at it as a math question unto itself, what it's really, well, I'm saying, I know we're about to wrap up right now. I'm saying question 9 really said, given and this is where we're leaving for today. Like, I'm not expecting to do anything more with this until we next meet. But where we are with question 9 is we're saying, given that, find x as a function of t. That's what question 9 says. What we just did right now in class, and it wasn't easy, right? I'm not even sure how many people actually did what I just did. I mean, but hopefully you see it now. But what we just did in class was a piece of this. What we just did in class, we did given dx dt equals 5t, find x equals function of t. I want to make this as clear as I can and then say goodbye. What we just did, like we have to do some math to do question 9. Again, it's math that we're going to do together. It's not math I expected you to have. It's math that I expect you to be equipped for. Like that's what all the prereqs are for. You're equipped to do this with me, the math of question 9. but it's worth taking seriously, because what we just did together right now is, instead of having a d2x dt thing equaling something, we did a one derivative version, like a first order, and I'll get the question in 1 second, so sorry, or if you have to go, so sorry. But I'm just saying, we did the one derivative version, but much more importantly, we just did the version where what we have here is a t. What we have to do together is do it when it's an x. It will be a different beast. That's what I'm saying right now, but sorry, Ardell, hand up, sorry.
Yeah, I was just wondering, is K over M a constant?
Oh, yes, totally. Perfect. Yes. It is literally, it's a constant divided by a different constant. It's like the spring constant, 200, divided by 0.3 kilograms, like in this case. But yeah, together that they make one constant, and that's totally how we're, and it might as well, that constant easily could just be 5 or something. Yes, absolutely. Perfect.
Okay.
Okay, cool. Right. So that's any other, so that's all I got for, I know. So we're on the, I'm leaving us, if this were a story, a movie, there'd be we're in suspense now, because like we're right in the middle of this. But again, with all y'all, I'm not asking you to do anything more with this. Like you could just set it aside. But that whole math methods, that whole homework sheet, especially the very first page of it, it's all practicing this idea from another angle. Like just take it with your own fresh eyes, but you'll see it's trying to get at it's asking you to take a bunch of derivatives twice so that you can see where we're trying to go with these second derivative things. But you don't have to do anything more with this until Monday. I'm going to stop talking. If you're good, I'm good. So anybody wants to go, just like, if you could just, yeah, say goodbye. Oh, bye.
I have another question.
Oh, sorry. Yeah, no, yeah, I'm here. Sorry. Yes.
Okay. So I'm thinking that in order to find the original function, the x equals function, like you have to integrate twice, right?
Yes, we are going to have to integrate twice. Yes.
Okay. So does that mean, so if you integrate this, won't you get a velocity function?
Right. Good.
Okay.
Yes. Except we'll keep going. There's one problem, but yes, you're on the right. Yes.
I was asking that because I was gonna say, if we could, like, if that were true, could I use one of the points in the question where we had the velocity and the position?
That's a really good question. Here's the thing. In the questions above, you can use the information from the questions above. It won't get you as far as it might seem, only because what they're telling you is the velocity at different specific points, like the velocity over here and the velocity over there. What we really would be desperate for here, what would be really helpful, is if we had velocity as a function of time. Like it's definitely true that if we had that.
Oh,
Okay. Yeah.
okay.
But yeah, no, but you're right. But yeah. That's but good question. Yes, but yes, you totally get. Yeah, I'm gonna stop. So any other? I'm here. If any other questions, or I mean, if you're, but I'm good. If anybody wants to just say goodbye, then say goodbye. Or if you want to ask a question. Awesome. Bye. Bye. So I'm just trying not to be I'm trying to be like the last person to go if I can, just in case of questions. So, but anybody who's still here, you can leave, like, we're done, we're good.
Goodbye, Professor. Thank you so much.
Thank you, guys.
Professor. Bye. Thank you. See you Monday.
Thank you. Yes, see you Monday. Thank you. Thank you. Awesome. Okay. Awesome. Thank you. Bye. Thank you. Bye. Awesome. Thank you. Bye. Awesome. Thank you. Bye. Thank you. And you guys are good. Prabhat or Leslie, question? Are you good or questions? Are you guys good? Or should I go past? Good, not good. Are you guys okay? Prabhat, Leslie? You're good, Leslie? You're good?
Yeah, sorry.
Okay, no problem. Do you want to copy anything down? Do you want, I can stay. Do you need?
No, I'm all right.
Okay.